All right. Picking up where we left off. The three big properties. Welcome back. 1 week from today, test. 2 weeks from today, final. Yay. Coming to an end. This is the last thing on our exam 4. So what I cover tonight is the end of exam 4. To Monday, we do a topic that will be on the final exam. And that's really it. But I'll kind of remind us that at the end of the lesson. But just so you hear it up front and at the end. So 1 week from today, exam number 4, and it goes up to what we cover here. Cool. These would be must-knows. So you're not going to be given these formulas, these properties. So highlight them, star them, make note that you do need to have them memorized. So logarithm of a product expands to what? The sum, yep. Kind of everyone's humming it, saying it. But yeah, a product expands to a sum of those two factors, m and n. And the logarithm of a quotient expands to subtraction, the difference. Fancy math word. So it's not too bad. And the third one really doesn't expand, but what happens to that exponent that's raised, yeah, brings to the front, becomes like a multiplier. Bless you. Cool. And every time we work kind of this way, it's called expanding. And if we go this way, condensing. Condensing, no. There we go. Condensing. Cool. And we did a few examples of expanding just to get us back in the mindset officially. And something a little more intense. Expand this expression. I think I need a sip of energy. No, it's not that bad. Another thing that came up as a reminder, specifically in this particular section, and always, but specifically right here, as you're doing your homework and for the exam, when we see any type of root, let's write it as an exponent. So that's going to be the first thing I do. I'm going to kind of go somewhere with this. So I'll say x to the 4th times y to the 1/3 power. Then we would say that the product inside expands to a sum, as I've just written. And I know in the homework they want one other thing. So technically we're done expanding, But they want us to write any stacked exponent, so base x stacked with a 4 here, as 4 times the logarithm. And same argument over here. We want to write that exponent as that multiplier. So a few things, nothing. At the end of the day, it's still really only 4 steps. One of the steps is changing any roots to an exponent. But if there are no roots, then you just expand your product. And lastly, bring down the multiplier. And that's your final answer. All right. Now let's work the other way. Condensing. Kind of very, very simple, something like so we just recognize that this is 1 log plus 1 log of something. So mash them together. And sums condense to multiplication. And we would have log 100. Arguably, nothing wrong with that. However, something to remind us from last lecture, if the base is invisible, what number is it? 10. All right. So most invisible numbers are 1, but this one is not. This is a 10. And then can we do this? Yeah, a calculator can do this, but how about without a calculator? What power of 10 makes 100? 2. So this simplifies all the way down to 2. So also a reminder from last class, the invisible base is 10. We call it the common log. Right? Questions so far? Pretty straightforward. Question about subtraction, but I assume you have an example. Yeah. What's your question about subtraction?
How do we know what goes in the numerator, what goes in the denominator when it's written like that?
The left goes on top, the right goes on the bottom.
That's always true.
I kind of had a hunch that was going to be your question. But his question was, what is going to go, let me just kind of preface this in case you missed what he's asking. What goes here versus what goes here? What's on the left will always go on top, and what's on the right will always go on the bottom. And that has a variable in it, so that's about it. We're done. There's nothing else to do there. Why am I having a hard time spelling today? Condensing. So the only thing that might be hard, I don't think it is, would be something like this. 2 So in my career, this is the only time students might have a mistake, but I've learned to add this sentence into my notes because I didn't always say that before. Some students will say, all right, this is obviously a plus, good. They're thinking product, multiply, also good. And then they do x times this expression. And that's not true. The reason that's not true, we can condense logarithms when there's a coefficient of 1 in front of them. To emphasize that, let's look at the property. 1 logarithm of something plus 1 logarithm of something condenses to their product, okay? No fear though, if there's not 1, we're just gonna bring it up. We're gonna use that third property, which says, hey, you can bring it down. Then we're gonna say, nah, we don't want it down, bring it back up. Oh, I'll also remind us too, just almost everyone was here, but I know at least one person was absent. Natural log is that, ln. So it's the only other logarithm that's kind of funky. So log with an invisible base is a base 10. ln is still a logarithm, and it's base e. So if you missed that last time, because there's a lot, but that's it. But other than that, still just a logarithm, has the same properties. Cool. Now that we have 1 natural log of something plus 1 natural log of something, we can mesh them together. X squared times the cube root of x plus 5, because I'm going to put it back in its cube root form. Why? Because I know my lab wants us to. And that's it. There's nothing else to do. We're done. Okay. So I'm not really going to do another example. You can use the view an example. I just don't think it's necessary. 3 properties, 2 of them allow you to expand. The third one says, hey, if you want to bring down an exponent, bring it down. If you want to bring it up, bring it up. Just a matter of applying it. All right. Okay. If you have a calculator, take it out for a minute if you want to. It's not necessary. And see if you have a way of doing this on a calculator. So by the way, the answer is, what is the answer? What power of 3 makes 81? Is it 1? Nope. Is it 2? Nope. 3 squared. Is it 3? Is it 4? It is 4. 3 times 3 is 9. 3 times 3 is 9. So there's your 4 3s. 9 and 9, 81. So the answer here is 4. Can your calculator get 4? It's not, as I said, not a big deal. If you purchase this one, or pretty much anything in the past, I don't know, 5-ish years, I won't say anything. Let me rephrase that. Some calculators still don't have this capability. This one does, and a lot of the newer ones do, but not all of them. So I think if I remember, log, you have to hit that log button 3 times over here. So the first time gives you natural log, the second time gives you the common log, And the third time on this calculator allows you to input any base you want. Base 3 logarithm of 81. And there's our answer 4. That's a lot of stuff. However, anyone not have that or not sure? Yeah, let me just see really quick. That one I know doesn't. That one I'm not sure. I'm going to say no. This one I don't think does. Nope.
I've heard 2 other calculators.
You might, it might. That one does? Yeah, I don't think it does the different base. And that's my point here. So, and you don't go buy a new calculator. So back on track in like 30 more seconds. So good, such a useful calculator, such an awesome feature for that purpose. But when I was in school, high school, like 1996, these calculators did not exist, obviously. There were scientific calculators, and they had what a lot of you have, the natural log and the common log programmed into them only. And so where I'm going with the story, your calculator, even without that base 3 or base whatever feature, can still calculate this using the change of base formula. So I'm just going to tell you what it, like I'm going to show you it, and then I'm going to put it in a big bold box. But the change of base formula says you take this and you divide it by this. You use the common log of 81 and divide it by the common log of 3. Actually, you could use the natural log of 81 and divide it by the natural log of 3. But you can't interchange them. You can't take like the common log of the top and divide by the natural log of the bottom. So I'll generalize that in a minute. But that's what the change of base formula says. You can take any logarithm and change it to a different base using kind of this property. So if you want to use base 10, use the base 10 of 81 divided by the base 10 of 3. Or if you want to use base e, then do base e of 81 divided by base e of 3. And just to confirm it, because there's one other thing to be careful of. So if you don't have the feature that I showed you, and you're going to use, and you're going to need to in your homework, what is important, your calculator will automatically open up a parentheses by default. So most of us will type in like log or ln. I'll just use ln. But notice a parenthesis opened up by default. You have to close that. I'm not going to, because I'm going to show you if you don't, if you're just like, oh, log or ln 81 divided by ln 3, might even give me an error. Definitely doesn't give you the correct answer. It gives you something close, but that's not, it's not 4.3. Go back. Log 81, close your parenthesis, divided by ln 3, close your parenthesis, and now you get the exact answer. And just to overkill this, if you wanted to use common log, it doesn't matter. You should get the value there, okay? So don't go buy a new calculator. If you're like, oh no, he said buy that one and I was doing so well. It's not really that big of a deal because you can do it. So that's it. So if I'm starting at a log of some base, it could be base 3, it could be base 5, it could be base 1/5. Then you can convert it to a different base, whatever you choose, what is probably going to be either 10 or E, but I'm just using the letter C because if some strange reason you wanted to change to base 2, and if you like binary, you might do that, but most of us won't have a reason to do that. But I'm going to say formally, you can change to any base you want. I'll kind of just slap this with the highlighter. Those last two are the most used because your calculators are programmed with base E and base 10 in them. And most teachers actually just use the last one for the most silly reason, but I kind of chuckle every time I say it. Because when they write it in their notes or on the board, it's only 2 letters instead of 3. So it saves them time. Okay. It doesn't matter is my answer, but okay, cool. I don't know what else to say.
So did the CC cancel out?
No. It's just standing for you can convert to any base you want. But it's not acting like a form of 1. So here's something we definitely need a calculator for. Well, I know this answer has to be between what and what. So 2 cubed is 8. So it has to be bigger than 3 because I need to make 10. But 2 to the 4th is 16, so it must be smaller than 4. So maybe I don't need a calculator. I know the decimal to that is more than 3, but less than 4. But if I needed more than that, I don't know anything else to do except pick up a calculator. Now again, if I have, or you have this capability, feel free to use it. And you get a number more than 3 and less than 4. And I'll tell you right now, it is super common, and it'll be stated to use like 3 or 4 decimals. So just be on the lookout for that. Pay attention to how many decimals you need. We definitely go more than 2. Just to confirm, if I wanted to use natural log of 10, close parentheses, divided by natural log of 2, close parentheses, you will get the exact same decimal. So for our note's sake, 3.3219. This is about 3219. The end. 4 properties, 4 big properties to know. Uno, dos, tres. Memorize. And change a base. Yeah, know it. Know one of these last 2, or both of them. Or what other professors say? ln of m divided by ln b, because it's less letters. All right, that's all. Any questions about anything from the end of last class or this with these properties? No? Anyone? Pretty good. Then onwards we go. Logarithmic and exponential equation solving. So the outline for the rest of tonight, and I'm not even sure I'm going to need the full hour. I feel like I say that a lot and then end up using 2 extra minutes, but I really believe I don't need more than an hour. So we're going to look at like solving equations. What do? Get the feel of it, learn it. Bottom line, whatever we do to one side of an equation, we must do to the other. But obviously we'll learn how to just see it with logs and exponentials, and then look at a couple more applications or some applications, and that's it. End of content for exam. Can anyone do it right now? What's the answer for x? I claim you really probably don't even need a pencil. So just by inspection, just by looking at it, what does x have to be? 8. I'm seeing a lot of head nodding. Yeah, let's check it. 8. What's going to happen to 8? It's going to get reduced by 3. It's going to become 5. And 2 to the 5th is 32. Yeah, cool. So that's one way to solve them. Just look at it. Not told in a textbook. But if you wanted a pencil and paper way, rewrite so that both bases are the same. So I guess we can imagine just saying if they're both the same base, then we can cross them out and say x minus 3 has to equal 5. If we add 3 to both sides, we get the answer that we found by just looking at it. So now we have a more paper and pencil way of doing it. So now let's play with fire. No, not really. Let's look at something a little more challenging though. Well, we learned something. We want to make the bases the same, and then we can cross them out. So please don't cross out 8 and 4 and say x plus 2 equals x minus 3. They're not the same base. Any ideas how we can make them have the same base? Like, is there any numbers coming to your mind? 4 and 8. Can I make 8 using a base 4? What a weird question. But can I? Let's look. 4 to the 0 is not 8. 4 to the 1st is not 8. No, we can't make that base become a base 4. And very similarly, I can't make this base become 8. 8 to the 0, 8, no. So I'm hearing it. We can't use base 4. We can't use base 8. Base 2. 2 cubed is 8. And 2 squared is 4. So we're going to take this 8 and call it 2 cubed. And we'll take this 4 and we'll call it 2 squared. Wonderful. What's true about stacked exponents? What's going to happen here? Multiply. So 3 times x and 3 times 2 is 3x plus 2. 2 times x, 2 times minus 3, 2x minus 6. The rest is going to be mad simple. And I don't think this was hard. You just have to see it. So example 1, we learned that sometimes we can probably just look and figure out the answer, but we learned a strategy. They have to be the same base. In this example, we said, oh, I need to figure out a base to use. And that can be the challenging, but I'll tell you this, it's going to probably be a 2 or a 3. I'll tell you for sure it's like a 2 or 3 or maybe a 5 because you'll see like a 25 just vibing. I don't have an answer for that though, so you just kind of get to think like, oh, 8 and 4, let me try 2 since they're both even and 2 goes into them. But it's not like a GCF or anything. It's just some knowledge of exponents. So that's why I said recognize like powers of 2, 2, 4, 8, 16, 32. Recognize powers of 3, 3, 9, 27, 81. Pretty much that's it. Now we can just go adios, amigo. 3x plus 6 equals 2x minus 6. Subtract 2x on both sides. Then subtract 6 on both sides. Yeah. I was making 0 in my head, and I'm like, no, the answer is not 0, and it's not 0. Negative 6, take away 6 is negative 12. And we're done. How did that get? Okay. Good by me. That's just strange. Yeah, we're in trouble. I won't make you stare too long, but just long enough to convince yourself there's no way we're making a common base. What are we going to do with 2? Okay, I'm waiting for suggestions. So we look at 7 and be like, yeah, that's not happening. So we give up hope pretty quickly. So we'll do 2 methods. Method 1, write in log form. So in last class, we introduced what a logarithm is. Log base b of something is something else, convert it into log form. So remember I said like you keep your base and change these things. So we get the base 2 logarithm of 7 is x. And that's what that algebra is all about. Boom, solve for x. We did it. Just like that. What? Yeah, that's it. Write it in a log form and be done. And then probably smack it in a calculator. I won't repeat the story after this one last time. So the last time is, if you got this feature, cool. If you don't, then use change your base. And either way, as you've seen too many times tonight, so I won't do it again, you get about 2.8. And we're going to use 4 decimal spots tonight. I think that's what my lab wants. It's either 3 or 4. So just, it'll say at the bottom how many decimals to use. But I want to use 4, 8, 0, 7, and then round to the next digit of 4. So 80, 74. That's pretty straightforward. Right. I kind of like that method, but it's not typically what most teachers do, and I understand why. So I'll cycle back to that shortly. But just to kind of lay it out, the second method would be take the natural log of both sides. Or the common log, but I'm going to do what a lot of professors do, use less letters. So I'm going to say ln of this equals ln of that. And then you use your property that says, hey, if you have an exponent inside a logarithm, bring it down as a multiplier. And then if you want to solve for x, you divide by the natural log of 2. Which, in case you forgot, is exactly what I did. Right there. It leads to the same answer. ln 7 divided by ln 2. Do you need to know both methods? Not really. In a way, this is the stronger one. In another example, I'll show you why. Although I do like this one because when it works, it's just pretty clean. Write it in log form and throw it in a calculator. Oops, my bad. Here's where method 1 kind of fails. So don't even bother writing it. But if I were to try method 1, I would say, all right, keep the base and swap all of this with this. So it'd look like the base 3 logarithm of 7x plus 1 equals 2x minus 1. And while we can go from here, we really could. We can take down this exponent, and then we'd have the base 3 logarithm of 7. It's just not what's done, right? So there is a way out, but let's just do what everyone else does. Let's conform. Which I need some down here. So 3 to the 2x minus 1 equals 7 to the x plus 1. And that's to take the natural log of both sides. And we're still going to pull out the exponent. So 2x minus 1 becomes a multiplier. And this is probably the most, it's not challenging, but it's going to be abstract. It's not challenging, it's just going to be abstract. We're going to distribute this exact form. We're not going to pick up a decimal right now, but we're going to treat this as an object. And we're going to distribute it and distribute it. And we're going to do that over here and here. So we get a 2 natural log of 3 times x minus a natural log of 3 and we'll get a natural log of 7 times x plus a natural log of 7. Abstract. It's like a Vincent van Gogh. Actually, that's not abstract. Who's an abstract artist? Who's like the most famous one? Who is it? That might be it. I can see the art, like there's like classic, like abstract art. But I don't remember that name, but that could be it. Okay. So I can help you see this. If we had an equation like this, what's our strategy? To do what? Yeah, get everything with x on one side and get all the number parts on the other side. So we need to do the same thing. Does this term have an x? Yeah, it does. But this one doesn't. On the other side of the equation, does this have an x? Yep, but this one doesn't. So let's bring this term to this side and this term to that side. We'll do it one at a time. So I'm going to add natural log of 3. Do not combine them, even though I almost... Those don't combine. Well, they don't combine to 10. I'm kind of fast forwarding here. How do we condense the sum of two logarithms? Multiply. All right, so as I said, there's a lot of moving pieces here. This is the one example you need to lock in on. Don't call that 10. We'll eventually call that 21, but not right this second. We're going to subtract. And again, don't combine things. ln 3x minus ln 7. And we will call this 21. I lost an X. Where'd you go? Right there. The next non-trivial, meaning most of us probably wouldn't have thought to do that on our own, so it's not obvious to do this step, is to factor out the common factor here. So you have 2 times the natural log of 3 times x minus a natural log of 7 times x. We factor it out. What can we do with this stuff now? We can condense it. How does subtraction condense? To a quotient. Wait a minute. We need 1 and 1. Damn, we don't have 1 and 1. So we'll bring up the 2. Three squared is 9. So I'm just talking that step out. And then we're going to have 9 divided by 7. Lastly, we divide by this number on both sides. And that's your final answer. Do not condense here. Another common mistakes. So this is a quotient. This is a quotient. But it's the quotient of 2 logarithms. So if you think back, because I don't want to scroll, but if you think back to the 3 big properties, it says if you have a quotient inside one logarithm, then you can expand it to subtraction. But this is 2 logarithms. Like we could expand this, actually it would go right back to up here. But there's nothing else to do here. This is your final answer. So some students get confused there, and I'm trying my best to say, think back what the first property says. If you have a quotient inside of a logarithm, you can do something with it. But this is not a quotient of 1 logarithm. We just got to carefully put this in a calculator. Natural log of 9. I'm sorry, that's not 9. Delete. Natural log of 21. Close parentheses. Natural log of 9 divided by 7. And you'd get about 12.1144, rounding to the 4th decimal spot. So definitely a lot of work there. And as I said, the hardest thing of the night. We're past that now. Everything else, easy. When you do your homework, definitely find this page in your notes or view another example. And that's why I did this too. So that way, if you view another example, it doesn't feel like if I did method 1, which I could have, you'd be like, wait, that's not what you did in class. So for this pretty intense type equation, I am mimicking exactly what the author has done. So that way, if you need another example, you're like, this matches up. Right? I don't usually put that on a test. So take a deep breath there, but I don't think that's a double negative. So I show it and I want you to practice it, but I don't think it's a fair assessment question. It's like a little too challenging. So in terms of studying for the test, I'm not going to put something that challenging on it. Something like this, or you'll see a few other homework questions, that don't take 18 lines of work. That's a more fair assessment question. Okay, onwards we go. That's, by the way, how you solve exponential equations. So I kind of want to just put a mini summary here. You can try changing the base. Nothing wrong with that. It's actually no use of logarithms. I could probably teach that in a college algebra course or a high school algebra 1 type class. We don't teach logarithms in those courses. You don't need logarithms. But something like this, you absolutely need to use logarithms. And there's 2 common methods. This is the most frequently used one, and that's a pretty challenging example there. So now log equations. I also have 2 methods for. Method 1 when solving exponentials was rewrite it in log form. Now, if you have a log equation, we're starting with a logarithm. Method 1, rewrite in exponential form. Keep your base, change those. 2 to the 3rd power is x minus 4. Two cubed is 8. So adding 4 to both sides gives us the final answer that x is 12. Just quickly checking it. I probably could have done that too. That was really method 1. Look at this long enough until you can figure it out. And you probably would have said, I know what's inside here has to be 8, so that has to be 12. 12 minus 12 would make 8, and then that would be true. But pencil and paper way, very similar to the exponential, just switches form. Method 2. All right, so for method 2, with exponential equations, we took a logarithm of both sides. So in a similar aspect, we're not going to take a logarithm of both sides. But I'm going to use a new word you might not have ever heard before. Actually, I didn't hear about it till grad school. So I went through undergrad math never hearing this word. And it turns out it's 100% true. Most people will just say, we're going to do something on both sides. We're going to raise each side to the power. Like, let's see, it's hard to say because I'm not raising it to the 2nd power. I'm not putting a 2 over here, but I'm putting a base 2, and these are going to become the exponents on base 2. So I forget how my professor said it because once I learned what it's called, I only use that verb. And this action is called exponentiate by 2. And the reason we use 2 is you want to use this base. 2 to the log base 2 of x minus 4 equals 2 to the 3rd power. So if I lost you, all I did was take the left side and the right side, and they became powers of 2. this base 2 and this log 2 cancel out. You're left with x minus 4 equals 8. Just like we had if we used method 1. X minus 4 has to be 8. Adding 4 to both sides, you get the same answer. And that's pretty much how you solve log equations. We're just going to look at a few more rigorous examples, but that's the idea of it. Either rewrite it in its exponential form or exponentiate to cancel out the base. All right, so I had a multiplier of 4. And because I'm solving an equation, I'm just going to divide both sides by it. There, gone. Now, similar to the last example, we have a logarithm equation, right? What's the invisible base here? So we're going to exponentiate by e. This and this cancel out. We have 3x equals e squared. Then we divide by 3. And I've said it a few times, but I'll say it again. E is it's like the number of calculus. No, there's other numbers in calculus. There are 1s, 2s, 3s, and 4s, and negatives. But for certain parts of calculus, E becomes the number. And so this is a common type of equation you would eventually kind of end up with after doing some calculus stuff and need to be able to solve it. What is that as an approximation? Just for the heck of it, e squared divided by 3, 2.4630. But I will tell you, in my lab, they do want so even though I just converted to a decimal, I probably shouldn't have even done that, but I wanted to. The reason being, E, you just have to kind of say, that's it. It's a number, just like if we had a pi symbol. Leave it alone. If someone says what's a decimal, you put 3.14 in a calculator or whatever. But it will say, make sure you give your exact form. That's this guy right here. Should it say approximate form, that would be this. But I know it's going to ask for the exact. Just the worst spelling. This is on the test and probably on the final exam too. So I told you that last exponential one, not usually a test question, a little too much, good practice. But this kind of wraps up this section, and then a tiny bit more, like a couple applications. So I still think I'm going to be letting you out a little bit early tonight. We'll see. All right, so before I show you the example, you're going to recognize it once I show you and you do your homework. You're going to say, right? Because you're literally going to see two logarithms with a plus or a minus. So you're going to scream, oh, if there's two logarithms, that's what the professor was talking about. I got to know to do this. Condense them. Then we're going to exponentiate. It almost always, not always, but almost always leads to a quadratic equation. So we're going to factor it really quick. It's not a hard quadratic. And then you must, like this is non-negotiable. I didn't put it there just to be cute. It's non-negotiable. You must check your answers because it is very highly probable, not a guarantee, but when we solve a quadratic, we get two solutions. When we go back and check, inside a logarithm can never be 0 and it can never be negative. And my quick proof of that, this is like, we're going to do it in a second. But remember, a logarithm's graph looks like that. But there is no graph when x is 0, right? This never crosses at x is 0. And there's no x values in negative world. So if you have a logarithm of something like negative or 0, it's not a solution and you discard it. All right, so let's dive into the example. Leave. You will leave the hard way. Okay. All right, so here we go. You're going to see it. You're going to say, this is what he's talking about. Use the properties. You see two logarithms, condense them. Just to remind you, this is 1. There's a 1 in front, so we are going to multiply x times x minus 3. So on the inside, we get x squared minus 3x. Check my work. Digest it. Right? So x times x minus 3. Distribute x squared minus 3x. Already see the quadratic building. Step 1. Step 2, exponentiate. Invisible base is 10. Yes. So we're going to exponentiate by 10. This and this cancel out. X squared minus 3x and 10 to the first power. That's a really big power and a really small base, but is 10. Step 3, solve the quadratic equation. So we're going to make one side 0. And I don't want to spend a ton of time factoring, but it never hurts to quickly review it. When you have a 1 in front, which we do, and you will, because not making it more challenging than it needs to be, right? So you should always have a 1 here. We're just trying to find two numbers that multiply to -10 and add to -3. I'm hearing it -5 and +2. So that means x could be 5 or x could be -2. Now, if you type that on a test, if you did no more, you're probably getting 50 or 60% of the points. But so if it was 5 points, I would take off -2. I took out 40% of the points right there. Not on the whole test, but for this one question. You'd get 3 out of 5 points up to this point because checking is non-negotiable. If x equals 5, we go back to the original equation. Is that negative or 0? Log 5. Is 5 negative? No. Is 5 0? No. So far, we're good. When I sub in 5 here and I take away 3, I know that's this number, but I'm just trying to say like what we're generally going to do, is what we get 0 or negative? So 5 is a solution. By the way, it is possible to have 0 solutions. You check, the first one doesn't work and the second one doesn't work. It is possible that they both work, or it's possible only one of them works. So I'm just going to emphasize checking is non-negotiable. But when I say check, it's not a hard check. We're just making sure it doesn't make 0 or negative. By the way, I could have stopped right here, even though it's mad easy to check both, but right here, hypothetically speaking, suppose this was 8. I'd say, all right, so far it's good. Only one piece of the puzzle has to fail. It's like doubly failing, but if it fails anywhere, it can't work. Done. So the final answer here is one solution, and that is x equals 5. One more to go. Typically requires condensing. We did that. You exponentiate, did that. Led to a quadratic. Yup. Easy solving. So it's not like this crazy quadratic formula or like splitting the middle. You should just be able to be like, quickly find the numbers. Checking's non-negotiable. All right, so put a little more gas to the pedal, just go through it a little quicker. But you look at this and say, oh, there's two logarithms. I want to condense them. They both have 1, so subtraction condenses to an inside quotient. Left side stays the same. Right side becomes a quotient. Step 1 is done. Step 2, exponentiate. The invisible base is e. Exponentiate by e. Exponentiate by e. E and log e cancel out. Oh, that's cool. We haven't seen this yet, but it is what it is. Follow the rule. E and log e cancel out. So on the left, we're left with x minus 3. And on the right, we have 7x minus 23 times x plus 1. It doesn't feel like a quadratic just yet, but we'll solve this by cross multiplying. So I'll put in 1 there. And then we're going to say 1 times 7x minus 23. And we'll say this times that. This times that. Oh, I sense a quadratic coming now. FOIL on the left-hand side. Distribute on the right-hand side. The 1, that was just silly, but it's there for completeness. Combine like terms, negative 2x. Oh my God, a lot of algebra. Make one side 0, so subtract 7x. And to keep this ball rolling, I'm going to add 23 in a single move. Ready? Subtract 7x minus 9. Add 23 minus, positive 20. Find two numbers that multiply to positive 20, but add up to negative 9. That does it. So therefore, x could be 4 or x could be 5, but I'm not circling either of those because checking is non-negotiable. Go back all the way to the original question. And if I sub in 4, does this make 0 or negative? So far, so good. Sub in 4. Does this make 0 or negative? How about 4 plus? No. 4 is a solution. Let's do it with 5. Not 0, not negative. 5, you're doing well. 35 take away 23 is a positive number. 5, you're doing well. And 5 plus 1 makes 6. 5 is also a solution. As I said, if you missed it, it is non-negotiable. No, you didn't miss that. I've said that too many times. But it's not always one answer. It literally could be 2. It could be none. It could be 1. You just have to check. All right. That section is done. Let's see. Application. Actually, I already built up some applications. What was the application that you watched on the, hopefully watched on the streaming video I did? What is it called? Compounding interest. Yeah. So we already kind of one application for both exponentials and logs, even though we didn't necessarily do it with logs, but was using a compounding interest formula. So when you do this section, you'll see a little more of that. I'm not going to redo it, but there'll be a couple more compounding interest type questions. So read through them. If you need a help, use the help or shoot me an email, but I bet you'll be able to do fine with it, even if you just view an example to refresh your memory, right? So there's a little flair, but I'm going to do an example too, and you should get the vibe of it. The other most common example is something called half-lives. And what a half-life is, it's like a true Earth thing, like scientists study this. Does anyone actually open up to the floor? What is a half-life?
It's like how long something takes to decay, like half of it to.
Yeah, like radioactive decay. I talked about an oil spills, so that's not a perfect example of a half-life, but I'm going to use it anyways. So suppose there's 100 gallons of oil in the water, and just naturally it like dissipates or whatever, goes away. It becomes 50 gallons, and let's say that takes a day. I'm just totally making something up. We would say the half-life of an oil spill is 1 day then. So if 100 gallons became 50 gallons, it takes 1 day for it to become half that. Right? But a true half-life is usually like things with gold. Like literally, if we want, unfortunate, I'm going to be grim for a minute, but if we left a piece of gold here, it would not really change its quantity in our entire lives. So like if this was a bar of gold, when you're 100 or whatever year, as old as you get to be, and I hope it's as long as possible, but it probably would be the exact same. But literally at some point on this earth, it would be shaved half, just naturally. Gold has a half-life. Everything has a half-life. Gold's half-life, man, look it up online. It's got to be in the millions of years. But just left out, it would eventually go away. So anyways, that's what a half-life is. It's also the most common thing to study is carbon, right? And I'm not going to pretend I know all of it, but trees kind of like suck carbon in, and they do something like with their rings, and they can, something called carbon dating, right? So they can find the amount of carbon in an object and then say, oh, so why did I use trees? It could be any object. I was just thinking trees. It could be any object, but they can find like the amount of carbon in it now and kind of work backwards to figure out how long ago it was on this earth. So typically like ancient bones or something like that. All right, so that's the little side story that wasn't 100% clear, but about what a half-life is. The half-life of can anyone pronounce that? What is that? Metal? Cool. I hopefully taught you something. You just taught me something. It's a type of metal. That's cool. We should do an experiment. Let's meet in 28 years. Someone go get some strontium. We'll measure its mass. Is that fair to say? And we'll meet again in 28 years, see how everyone's doing, and we'll weigh that thing. Like that would be the most fun thing on earth. Oh, okay. So that'll really be fun then. We'll see what happens if we're okay. So blah, 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 blah. If there are 60 grams originally, how long will it take to become 10 grams. All right, I think I might be right on my hour mark, but this is the only example. First, here's an equation I would give you. Anyone remember the formula for compounding continuously? I said it's like, I call it the PERT. P, which stands for like the original amount, your principal, times E raised to a decimal times time. I give you PERT. This is your original amount, but we're not in finance. But this right here stands for your original amount. There's E. R stood for like your percentage, but this time we're saying it's some decimal, and that's time. Like, but it's just going to be some decimal, all right? But I would give you this, but I just want you to recognize it's what we've seen before. So really quickly, your final is equal to your initial times e to the kt. We don't have k. We only have two pieces of information. We know this. We know that it's going to take 60 grams originally for it to become 30, which is the half of the original amount. Is how long? 28 years. See where I'm going with this? The first sentence says the half-life of this radioactive material is 28 years. So if I'm starting at 60, I'm going to make half of 60 30, and I know it's going to be 28 years. What we're going to do now is find K. Then we take K and we kind of do this a second time. So let me go through it. I'm going to divide both sides by 60. 1/2 equals e to the 28k. Think about that. Make sure you believe that. Divide by 60. How do we solve an exponential equation? This is an exponential equation. Well, we can take ln of both sides. ln of 1/2 equals ln of e to the 28k. This logarithm and this base cancel out. Because they're the same base. So you have ln of 1/2 equals 28k, and dividing by 28 and using 4 decimal spots. Negative 0.0248. 0248. Now we go back and answer the big question. How long will 60 become 10? We want to output 10 starting at 60, and we use our answer, for K. Negative 0.0248. Times T. See the difference? In this first time, we needed to use the half-life information to find K. Then the second time around, we use the K to find T, and then we're done. So we're going to divide by 60, you get 1/6. We're going to take a natural log of both sides. The E is going to cancel out. And we're going to divide by this decimal. And we'll approximate it. I'm going to kind of just do something a little clever. ln of 1/6. And I'm just going to say divided by my answer right up here. Copy and paste because I don't feel like retyping it. And we'd get about 72. And here, it's going to say round to the nearest year, like because we're talking about a time. So about how many years? A little more than 72, but we'll say 72 years. That's it. That would be the time. And that's the end of our content for exam 4. I'll let you go in 1 minute. But briefly, if in case you missed it, I said in the application, when you open it up, you're going to see something about continuously compounding, and it's going to have vibes of this. It's going to say, like, how long will it take? So you're going to sub in your decimal, and now you just solve for T. You take both sides, ln, bing, 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 done. And then you're going to see a couple half-lives. And you can guarantee you'll see that on the exam. I'll have the review for exam 3 ASAP, maybe even tonight, but tomorrow for sure. So I'm just going to keep that as ASAP. We still don't have the exam for a week, so I'll see you on Monday anyways. Adios. Well, 4, right? That's the next one. And then I'll have the final exam right after that too. But it's crunch time for you and for me.